I'm going to talk almost technically. I'm going to try to show you what it is that they do in this country and that they do in foreign countries when they teach mathematics. Now, the thesis I come in with is a little different than some people think. Mainly, as far as I can track it, math instruction in this country has never been successful. And I mean, I've tracked that back 120 years, and Li Ping Ma has tracked it back 150 years. We have reform mathematics, we have traditional mathematics, doesn't matter. 0.5% difference in outcomes. Not significant when we're comparing against the people we're competing with now. And what I'm going to try to show you is what these people do when they do mathematics. So let's see here. Okay. So these are facts that will just fill in a bit on what everybody has been saying. And the point is that there's no doubt that college is the entry level into jobs now that mean anything. And so we have to think of college as the goal of the K-12 system. Now, since I'm involved with NASA, I thought I'd show you some data about NASA. So there's been some reference to the age of our employees in this country. I thought I'd show you over the past 10 years what the age distribution of scientists and engineers at NASA looks like. And as you can see, now the way this is set up, the corresponding dots here are the same age group, so 10 years ago, 5 years ago, and about 8 months ago. And you notice this, they're hiring at the highest age groups. And then they have a little difficulty hiring in these further out age groups. There's something called retirement that gets in the way. And the curve gets steeper and steeper. Now, they're not hiring down here. Now, I don't want to talk about the reason for that, but that was a slide that I did out of NASA data. This is a slide, that at the NASA Advisory Council meeting last week, the Generation Xers at NASA, they're panicking about this. They produced this slide. Back. So as you can see, the younger workforce at NASA is at an all-time low. And again, this is supporting this, and this is supporting what Craig was talking about. If you look at the total master's degrees in engineering by year, then this is the sum of from here on out of two components. This is a component of U.S. master's degrees, and these are master's degrees to foreign students. And you see what's happening. And remember, we're talking about preparation for the most attractive jobs in the economy. So Craig and Intel and these other companies, they can, with some difficulty because of the H-1B visas, they can hire this population here. But you see, NASA can't. As a government agency, NASA has to hire U.S. citizens. And that data that I showed you is what it looks like for our real workforce. As has been repeatedly said, math is the key here. And as Bill has said, we have tried to fix a problem that we're well aware of by putting more material in the lower grades. After all, shove it in, keep it going sooner or later by some kind of osmosis. Some of the kids are going to get to a higher level. What have we done? We've added data analysis, statistics, aspects of new math, including problem solving, Euclidean transformations, simple combinatorics. All has been added to the curriculum K through 12 since I was a kid. What's happened? Nothing. Okay, we're in Maryland, so here's a Maryland problem. So look at the sequence below, 2, 6, 18, 54. What is the 8th number in this sequence? Well, if you don't know, you're not alone, because I don't know. I haven't got a clue what the answer to a problem like this might be. There's no data telling me anything here, and any answer I give is simply a guess. But Maryland's not alone. This is a problem from the NAEP. So a problem from the NAEP. At 1 month, the puppy's weight was 10 pounds. At 2 months, 15. At 3 months, 19. At 4 months, 22. The question is, if the pattern of the puppy's weight gain continues, incidentally, that makes no sense. I don't know what that means. How many pounds will the puppy weigh at 5 months? Okay. I mean, I told you mathematically what the situation is. I have no idea what they're asking mathematically. However, Jerry, I do know what they wanted. They want to say, okay, the difference between the two, so you're looking at what are called first differences. The difference between the first two is 5. The difference between the next two is 4. The difference here is 3. So naturally, the difference here ought to be 2. So it ought to weigh 24 pounds. All right, fine. Of course, you've got no justification for that, but let's pull this a step further and say, okay, what about at 6 months? Well, the weight gain was 2 pounds here, so it's going to be 1 pound at 6 months. So it'll be, what, 25 pounds. At 7 months, well, there won't be any weight gain. What happens at 8 months? It's going to lose a pound. And at 9, it'll lose 2. So the question is wrong. I mean, the real question is, when does the puppy disappear? This is the quality of mathematics on the NAEP, the nation's report card. Recently, we're all aware of this, and in desperate circumstances, desperate measures. So the NCTM and the math community, yes, you skip, I know, decided that they would cooperate and try to put together some rational kind of answer to this problem. And the result of that effort was the NCTM focal points. And now this is aiming more toward what it is that's done in foreign countries. 3 major topics per year. And when one looks at the overall structure of the focal points, they align very well with the structure of the curricula in the high-achieving countries. Now, here's basically what happens. When you isolate out the topics in mathematics that are covered, there are just 6 of them. Numbers, number operations, and place value. Fractions and decimals, ratios, rates, percents, and proportions. The 4th is algebra. The 5th isn't showing. Functions and equations, measurement, and basic geometry. That's it. These 6 topics are in this focal points and in the curricula of the high-achieving countries are the content of the first 5 or 6 grades. Okay, but it isn't just to focus on fewer topics. These topics should be learned as mathematics rather than as vocabulary or factoids. What I regard as instruction in this country, and again, I don't care what curriculum you're talking about, I call it mathematics as lists. All it is a memorization procedure, memorize, fact, 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 regurgitate. Since there's no coherence, no structure, forget 6 months later, and start over again the next year. So now I'm going to show you what actually happens. So here we are in a better than average textbook and a typical kindergarten lesson, and the teachers in the audience can confirm that this is typical. So what's going on in this lesson? Well, that's what's going on. The kids are being taught an exceptional conjugation of an adjective. And they continue. Here's another lesson from the same kind of texts. What's going on here? Well, the kids are learning the first four numbers. Well, what are they learning about the first four numbers? First of all, if you look at your 10 frame, that isn't numbers, that's filling boxes. And why should you end the thing by putting in 10? It ends. So somehow it becomes a contest. So you're creating a contest here. The other thing that's notable, you can't see this well, but this is O-O-N-E, this is T-W-O, this is T-H-R-E, and F-O-U-R. What are they doing? Handwriting, printing actually, and vocabulary. They're conflicting or confounding mathematics and reading. So the lesson is not focused. Concepts are diffused by vocabulary. Now I'm going to show you one of I think this is the second lesson in the first grade text in Russia, 1984. Now, notice one thing right away about this lesson. There are no words. They are going to do mathematics. They are not going to confuse it with words. Mathematics is not words, it's concepts. What are the concepts being learned here? The number 1, the number 2. Now, these are numbers, and the only property of these numbers, well, you think the only property of the number is the counting aspect of it. Actually, it'll turn out that they believed, and I think correctly, that for small numbers, the counting aspect is hardwired. And what they're actually going to be doing is leveraging that hardwiring to make these into numbers as distinguished from counting objects. Look what happens in the next lesson. And you can see page 6, this is page 6 in there. Keep track of that so you know that I'm not cheating you. Okay, here is the next lesson. This is page 7. What are they doing? They're giving the kids the properties of the numbers 1 and 2. And what properties? Not that it's one object or two objects, but that 1 is less than 2. 2 is greater than 1, and 2 is equal to 2. They're developing the concepts of comparison with numbers that the kids understand intimately. So they're leveraging what the kids bring to the table to give to these kids instruction on what a number is. Next lesson. They add 3. And they carry through the comparison. 3 is greater than 2, 2 is greater than 1. Lots of examples of 3s. And the next lesson. And it is the next lesson. That's page 9. So I'm not cheating you. What have they done? They've introduced addition. And they've introduced subtraction. With the numbers the kids can understand. They've given these kids the concepts without confusion, without anything getting in the way. They have put the foundations together for these things as numbers as distinguished from simple counting. Now that's at a whole different level from what we do. So here we are, a continuation of the lesson sequence I showed you earlier. And at this point, the kids have gotten to 12. Well, the kids in the Russian system don't get to 12 for a very long time. But as you can see, somebody can now say, a teacher can say, or a parent can say, or a school leader can say, well, our kids are doing just great. They've got the numbers through 12, and their competition only knows the numbers through 5. But in fact, what they really know are just words. The numbers they don't know. You've seen what the numbers are now. One more problem here. This thing just kind of drives me nuts. So this is place value, and again, any teacher in the room knows that this is canonical. Every book has this page. Okay, so I say it drives me nuts. Why? Well, look what they're doing. Your ones, your tens, your hundreds, your thousands. What are they trying to get at here? Well, 1 is a point. 2, 10 is a line. 100 is an area. So you've got this area, you've got this volume. What are you going to do for 10,000? I don't think the kids are going to understand a tesseract. And there are other problems with this thing. The confusion, the same confusion we saw before, is evident in this lesson. Let's compare that with what goes on in these foreign programs. And then, again, you want to understand what it is they do, how they're doing it, and why it's so effective, and why what we do is not. And the best way to do that is to go through this. Okay, let's look at the models here. I should say one thing about this. The biggest reason, aside from the silliness of changing dimensions each time you change a power of 10, aside from that, the thing you lose when you do that is you lose any sense of magnitude. They don't see the number 1,000 as bigger than 100. They see it as different. Now, I'll show you what happens in the Russian program. First of all, ones are sticks, so are tens. They're just bundled. And I won't go through these problems. But now the next lesson, they show what the meaning of place value notation is. Why you use 2 symbols, a 2 and a 0, means 2 bundles of 10, 1 bundle of 10 and 2 ones. Here, this is a beautiful problem here. Measure the length of the strips in decimeters and centimeters and write down the numbers you get. And so what they're using is a meter stick as a model for two position place value. And the kids work in meters in those countries, and so this is completely natural for them. Tying it into the number line, tying it into their experience. Okay, a little further on, they now get to numbers to 1,000, and notice nothing changes. We take 10 bundles of 10, bundle of 100. It's 100 sticks. So the kids can feel the magnitude. You can visibly see and feel the magnitude of 100. Now we're going to break 10 bundles of 10, and you get 1,000. But it's 1,000 sticks, and you can see and feel the magnitude of it. And, with this kind of focus and this kind of care in a program, this is the result 2 or 3 pages further on from that last lesson. Here are some typical problems that I thought you might like. And this, I emphasize, is toward the end of the 2nd grade text in the Russian curriculum. So let's look at one of these problems. A bakery used 48 bags of flour in 3 days. How many days will 80 bags of flour last if the rate remains the same? What would our 6th grade kids do with that problem? So Bill says 2 years. It's way more than that. Unfortunately, sometimes this gets personal. So this is a picture that my daughter sent to me of my unique grandson's work about 3 weeks ago. In everyday math, if you need to know. And it depresses me. It depresses me no end. He's in 1st grade. This is what they're doing. If one is interested in this sort of thing, I've produced, and it's freely available on the web, I produced this monstrous book, which is the mathematics pre-service teachers need to know. And it's available, you can download it. This is the URL for that. More recently, the material I was just talking about is the content of a course I'm teaching now at Stanford. And some of the lecture notes for that course are also up, which give much more detail on comparison of how our country and the high-achieving countries do this sort of work. So there you are.
Thank you. Terrific.
Cheryl Jaffe, I'm a radar engineer with Northrop Grumman. And I have a question for Dr. Milgram, since you indicated some knowledge of a little bit of history of U.S. math education. And this is actually something I've been wondering for quite a while and not been able to get an answer to, so I'm kind of hoping I'll have some luck. When I've done tutoring in classrooms, I was actually a math teacher for a year, middle school, high school math. I took that praxis too. And when I tutor middle school students, I ask them, you know, what's the algorithm for converting a mixed number to an improper fraction, and everybody can recite it and use it. But they don't know why. They don't know why it works. It's fairly easy to prove. And what I'm wondering what this has to do with history of math education is one of the greatest math texts of all times, Euclid's Elements. You know, the classics are classics for a reason. Why have they been abandoned? Why are they not? When were they abandoned?
I had an absolutely horrible geometry course in high school out of Euclid's Elements. It wasn't Euclid's Elements' fault, but the teacher decided that we were capable of learning it on our own. And so, you know, so it's always been the weakest subject that I have. But Euclid's Elements were still present in the mid 1950s. There was a new math period in the 1960s through early 70s where it was decided to modernize the axioms, the Euclid's axioms, and replace them by the Hilbert axioms. There are sound mathematical reasons why one wants to do this. They are darn near advanced graduate level, of course. Anyone that sees a need to replace the Euclid axioms by the Hilbert axioms in high school is somebody I would like to meet and listen to. But somewhere in this period, the new math period, they changed focus to the Hilbert axioms, and then, you know, when the new math was discredited, somehow they didn't go back anywhere. What they did was they threw out what had been thrown out, added tiny bits of the wrong stuff from the new math, and just continued.